Hey guys, this is Dex and you're in the engine room. This is the intro video to my new Patreon channel where I'll be hosting much of my educational content about data engineering. What is a data engineer? A data engineer is a high-tech plumber. We build oil refineries, but for data. So anywhere in the tech world where people are having to ingest and clean and collate and transform data sets at scale so that, for example, analysts or data scientists can get a crack at that data. Typically, you'll find us at work building data pipelines to do just that. In my day-to-day work, I use what I call the Mercury method to build data pipelines. And in my instructional content, we'll be talking about building data pipelines using the Mercury method. So it's fair to ask, what is the Mercury method? The Mercury method is a set of patterns and practices in data engineering that I've developed over the years, along with an open source toolkit called Mercury, and you can look that up on GitHub. And the Mercury method is characterized by the following: very short intervals between inputs and outputs. That is to say, in the Mercury method, we tend to set things up such that we can make a change to our code base and then see the results of that change right away. I take a pretty dim view of some of these data engineering managed services from certain cloud providers who will go unnamed, because those feedback loops tend to be very long. It shouldn't take you 5 minutes or 10 minutes from the time you make a change in your code to actually see what the results are. So in the Mercury method, when we build data pipelines, build ETL pipelines, we tend to try to make those feedback loops as short as possible. The Mercury method also emphasizes small, sharp tools. The idea being that you want a collection of tools, software tools, each of which does only one or two things. And then we compose those tools together to accomplish more complex objectives. But each one of our tools is very small. It's very easy to understand what that tool does. In the Mercury method, we tend to compose our data pipelines out of smaller pieces. For the same reason, it's very important when we're trying to build good software quickly. We want it to be easy for ourselves or for other people who are looking at our code to break things apart so they can get a handle on what's going on, they get their bearings, right? So our data pipelines are not monolithic, they're modular. Make your structured data complex so that your logic can be simple. We're trying to look at things as much as possible in terms of lists, structured data, and functional transforms. Emit a piece of data, transform it, write the transformed data somewhere, and then write the next stage of your pipeline to take that transformed data and maybe perform another transform on it, and so on until your data pipeline is complete, until you've landed your data set where you need it, typically in a database. In the Mercury method, we try to automate things as much as possible, especially the small things that increase our cognitive load. We don't want to have to think about low-level problems. So wherever we can automate something in a way that's sensible and readable, we do. Here's an example of a Mercury data pipeline. This is a makefile. For those of you who are familiar with Make, you know what you're looking at. For those of you who are not, each of these units is a make target. The make target is composed of a series of shell commands. So you can literally copy and paste this and run it at the command line. And when at the command line, you say make and the name of a target, Make will simply run this series of commands for you. All the principles that I talk about when I talk about the Mercury method are on display here. Because I'm using this make file and I've got all my commands that I run right in front of me, I can easily change the command syntax and drop to the command line and run that target and see the results. You can see that in my make targets, I'm using small, sharp tools. Each command is relatively simple, and I'm using these command line tools, some of which I wrote, like chunker and looper, some of which I didn't, to get results. And again, because each of these data processing tools I'm using is very simple, it's very easy to see what's going on and to get my bearings in the code. It's obvious that this pipeline is also modular. The entire pipeline, when I run this actual pipeline, I run it as a make target, but that pipeline is composed of other make targets. So when I say make pipeline voter data, it's going to first prep the voter data, then it's going to prep the voting history data, then it's going to merge those two record sets, then it's going to ingest the voter data into my database. I make extensive use of structured data when I write my pipelines. In the ingestion, in the data ingestion piece, let's see, if we go here, no, it's not template, it's temp data. In the data ingestion piece, I use something called a manifest. This is the generated piece of structured data. I generated this in the pipeline itself, and it's simply structured data that encapsulates the commands I'm running against the pieces of data that I've chunked out. It's a very large data set, so I'm chunking it up into pieces so I can ingest these files in parallel as opposed to having to do everything serially. And of course, automation is baked in because all these commands, including kind of convenience commands like dblogin, kind of encapsulate command lines that are a pain to type and retype. So for example, when I want to log into the database, I don't have to remember all these command parameters. I can just say, make dblogin, for example. Now I'm logged into the database. I'm always harping on the concept of reducing toil. Here, I am, for example, changing the names of fields such as voter ID org, state ID, what have you. I can map and remap the field names very quickly, and then I can drop to the command line and rerun the command. I can try a mapping, and then I can right away see if I like that mapping, if I'm getting the desired results, and I can jump back into my IDE and continue to make changes. The Mercury method is not something new. I started to develop the Mercury method when I started looking back in our history as software engineers and started looking into tools and the patterns and the practices that people used decades ago to come up with the Unix operating system and the tooling around that system. Of course, today we use Linux. That's the most kind of popular operating system in the data center. Linux is just a clone of Unix, but there was a philosophy around the creation of Unix, and that philosophy informs everything I do in my practice and with the Mercury method. The Mercury method is not magic fairy dust. We still have to work hard. We still have to keep our eyes on things. We have to be attentive. No formula, no system, no tool relieves us of that obligation. The Mercury method is more like a force multiplier so that our hard work moves the needle more and that our vigilance is rewarded, but we've structured our projects so that our vigilance can be focused on the important things. And we're not spending a lot of time chasing down bugs, chasing down errors. Our code base is easy to manage. It's not foolproof. It's possible to make mistakes. It's possible to write bad software using the Mercury method. It's just that the Mercury method tries to set things up so that errors, especially simple errors, cause things to fail fast and in a way that's very obvious. But you still got to sit, you still got to think, The point is that, again, you want to be thinking about high-level problems to the extent that that's possible, and you want the tooling to take care of the low-level problems for you. So again, we push down on that cognitive loading so that we can focus our attention where it does the most good. Mercury is a collection of open source tools, but the Mercury method is not simply those tools. And you don't have to use all of those tools or even any of those tools to employ the Mercury method. This is very important. If you already have a chosen data engineering practice, if you have the way you like to do things, or if you're at a company where they like to do things a certain way, you can pick and choose among different practices that I'm going to talk about in this method and use them as force multipliers where they make sense for you. I've written all my tools to play nicely with other tools, and really, as long as you have tooling that plays well with the POSIX file system, that plays well with the kind of three basic communication files, standard input, standard output, standard error, then you have a shot at using Mercury to move the needle for you and to be a force multiplier for you. The Mercury method isn't all or nothing. As I've said, you don't have to buy into every single tenet of Mercury to get wins, right? Or to have it be useful for you. Why should we use the Mercury method? And why do I use it? Well, for example, why do we need short feedback loops? Well, in computer science, we have a saying, which is context switching is expensive. Those of you who write parallel software, for example, know what I'm talking about. There's a reason why we tend not to spin up 1,000 threads, for example. Having to change context is expensive. So the idea is if you have to put in a change in your code and then jump away from the terminal or from your IDE and go now to a web console and click around and then wait for something to happen, now you've had to switch contexts. You were in the code, you were in the data, now you're out of it, now you're somewhere else trying to see what your results are. And I think that's bad. So the focus in Mercury is to try to keep software engineers, data engineers, in the code, at the console, at the terminal, in the IDE, where we are most productive. Good ideas about software are wonderful. Innovation in software is wonderful, but none of it matters if we can't get the job done fast. Speed is wonderful for winning the argument. Speed is wonderful for giving your stakeholders, and in the case of data engineers, our stakeholders are usually analysts, right? Or they're data scientists. Our stakeholders are often people who don't really care about code. They care about insights, right? So they are not going to be impressed by the tooling on its own merits. They're going to be impressed by the tooling and by our methodology based on how quickly we can get back to them with results and how our working method gives them a sense of control over the process. So speed is the key. Short feedback loops help us work faster. Code that fails quickly and obviously when something goes wrong, and something will always go wrong, can be fixed more quickly. So to the extent that we can write data pipelines in a way where our failures are obvious, that's better for us. That tends to be a win for us. So as I said earlier, this is a Mercury data pipeline. I can show an example of short feedback loops by digging into how I'm prepping the voting history data. Right? This is a make target. It's part of a larger target. It's a modular piece of a larger target that actually runs my complete pipeline, right? So I'm going to prep the voting data. I'm going to prep the voting history data, so on and so forth. And each one of these functional units is testable in isolation, okay? And then if we dig further down, we see, hey, I'm running the xfile command. The xfile command is mapping field names from the input data, the raw data I downloaded from the Ohio Board of Elections, and it's outputting that data to a file. Note that X file is not responsible for writing files. It doesn't have to be. It writes its data to standard output, and then I can use the built-in redirection primitive to write that data to a file. So the tool is as simple as possible. It does one thing. It maps input structured data records to output structured data records. And then when it comes to tweaking the code, figuring out what kind of mappings I want, I can jump right into the config file for X file, and I can change a mapping, and then I can run this command. And if I want, I can say, let's see, what's the syntax for X file again? So if I want, I can say, I can limit this to only 5 records. My input data set is somewhere around, it's around 1 million records or so. So I can process a very small amount of data, tweak my settings, and when I'm ready, I can remove the limit switch, let it run to completion. This is a small thing, but these kind of small gains add up over time. We need small, sharp tools so that we can respond to consumer requests faster. And again, when I say consumers, I'm talking about our stakeholders. As data engineers, we are working hand in hand with data scientists. We're working hand in hand with analysts, forecasters, again, people who are trying to get insights from data. And when we use small, sharp tools and we can compose kind of more complex pieces of software, that means, again, something goes wrong, we can break those composed solutions apart and figure out what's going on. So to the extent that we can respond faster to our consumers inside the company, wherever we're working, that's better. Small, sharp tools make things inherently testable because, again, each tool only does one thing. So the space of your testing criteria becomes smaller. Is this tool doing the right thing? If the right thing can be easily defined because the scope of requirements is very small, it's easier to test the output of that tool to see if it is doing the right thing. Software development is characterized by something that's been called the downhill synthesis, uphill analysis problem. Simply put, it says that it's easier to create new code than it is to read code that's already been created, right? So when you're synthesizing code, gravity is with you, you're going downhill. When you're trying to figure out what's been written, it's much harder. So the smaller your tools are, the less code there is, the less complexity there is within any given tool. So it's easier to analyze what the code is doing, if bugs creep in, if the specification changes, if you make an error, if you do something wrong. So here's another data pipeline I've written. This one is called Lex. And same thing, my the focus of action is always the make file. That's where the rubber meets the road. So if someone knows how I write pipelines, they know that if they want to see how to get things done, they basically start by consulting one file. That's the make file. And the targets in that make file, these functional units, completely define everything my data pipeline does. And we notice here I'm using this principle of small, sharp tools. Here, for example, I'm normalizing my input records. And you notice I'm in these couple of lines, for example, I'm not even using any tools that I wrote. I'm using tools that are part of the shell, cat. I'm literally emitting a file to standard out, and then I'm piping the output of that command to the sed command, the stream editor command. And then I'm using the file redirection primitive to send that data to a file, right? So That's the idea. As long as all our tools function well, play well in that ecosystem of standard in, standard out, standard error, then it's not necessary to use a tool that is actually a first-class Mercury citizen. All these tools play nicely together, and I can use tools from any and everywhere to get the job done. But each tool is very simple, right? And it's very focused. And because I'm journaling the outputs of my processes, it's easy to figure out what's going on. It's easy to figure out, when something goes wrong. You have files that you can inspect, and you can see what's happening, where the errors are, if errors have crept in. Why should data pipelines be modular? Again, they're easier and faster to debug. You can respond to changes more quickly. And again, this gives our data consumers confidence in us and confidence in our solutions. They're more maintainable because, especially in data engineering, it's very common that the specifications will change. The probability that someone will send you dirty data is very high. You don't want to have to dig around in hundreds of lines of Python code in one module, for example, to figure out what you need to change to respond to an external change that's been imposed on you, right? So data pipelines are modular. Those modules can be simpler, and it's easier to figure out what's going on. Talking about modularity, here we're back in the Civics data pipeline stack. And again, the actual pipeline is not monolithic. It is composed of a series of commands, a series of make targets. And each make target is itself composed of a series of commands. So we can run the whole pipeline by saying make pipeline voter data, but we can also run these commands individually, and we can test them individually. So modularity from the ground up. Why should we think in terms of lists, structured data, and transforms? If you think about the operating system as infrastructure, then you see right away that the Linux operating system, which is really a clone of the Unix operating system, and uses the principles baked into the Unix operating system and the POSIX file system and the shell and so on, you find that we're already in the best possible environment for handling lists and structured data and doing transforms. And we're going to go into this, when we start doing some live coding. But the idea is that there are many tools that have been around for decades. They're old. They're very stable. They've been pounded on forever. And those tools are there for us to handle lists and generate structured data and transform records from one form to another. To the extent we can leverage those tools, that's good because we're controlling risk. New code equals risk. We always have to write new code, but the point is that if we can get things done while writing less new code, that's better because it's less risky. Our logic can be simpler. Again, this goes back to that fundamental philosophy of making your structured data complex so that your logic can be simple. Again, I keep harping on this notion of speed. Speed is the key. The ability to test things, and the ability for people other than us, or for someone other than the author of the code, to get in there and manage the code. If our sight lines are clean, if the code is easy to read, if we don't have a lot of baked in complexity, then people who come after us and have to maintain a code base that we've stood up have an easier time. And look, we'll have an easier time. If something's on fire in the data center, we get the call at 1 a.m. If you have to manage a large amount of complexity, you will be less efficient, you'll be less effective than if you're looking at something that is relatively simple and therefore easier to understand. So Back in the civics data pipeline stack, we're talking about structured data, lists and structured data. So here, and later, it's not important right now for you to understand what each step is doing, but just understand how I'm doing it. So what am I doing here in this part of this pipeline, in this part of the ingest phase of my pipeline? Well, what I'm actually doing is creating lists. And we can see that I'm creating lists because you can just look at the output, right? So when I generate data sets in the course of running a pipeline, I typically write them to a directory called temp data, right? And you see chunked voter data files .txt. So if we look at that, that's a list, right? And then we see what else is happening. Voter data ingest commands. So again, we look at temp data, voter data ingest commands. Here's that list, right? And then we go here and we see I have another file here, chunk index. If we go here, we see chunk index.txt. Very simple. And here I have another file that I'm generating, voter data ingest out files, the output files. And again, we go and you see I'm just generating file names is all I'm doing. And here is that list of output file names. And then after I've generated these lists, and they're very simple lists, it's easy to see what's happening, then I use these two Mercury tools. These are the tools I use very commonly in conjunction with each other, TupleGen and Tuple2JSON. TupleGen takes a collection of lists. It glues them together into what is essentially a headless CSV file. So you can think of the inputs as actual columns of data, and the output is an entire file consisting of all those columns of data lined up side by side. Okay, it's a CSV file without its header, essentially. And then I pipe the output of TupleGen to Tuple2JSON. Tuple2JSON will now take that file, and it will assign column names, okay, and then it will write that out as JSON, right? So right here we have two commands snapped together by the pipe primitive, and then the output is structured data, and we see voter data ingest manifest, and if we go look at that, that manifest is just a JSON file, right? And it's a JSON-L file, one record, per line. So again, in the civic stack, we've talked about using lists and structured data to get things done. And then part of my automation strategy, and this is a pattern I use very often, is to now take that structured data, that manifest, and use it to generate code. And that's exactly what I'm doing here. So I have an empty shell script, right? If we look at template files, this is just the header for a shell script, nothing else. So I copy that empty shell script into position, and then I'm looping over this piece of structured data I created. And now the task is very simple. I'm saying loop over this manifest file and then generate a string. And the output string is the command field from this piece of structured data and the out file field from this piece of structured data. And so this is like a template string. So I'm using structured data, and then I'm feeding that structured data into a template, and then I'm feeding those results into a shell script file, so that when I'm done with this, what I end up with is, let's look at temp scripts. I end up with a shell script that's ready to go. So these are core ideas in the Mercury philosophy, the Mercury method for building data pipelines. Why should we think about things in a way that's automation forward, in a way that privileges automating small tasks? Small tasks add up to large expenditures of time. You know, it's the things that you do 50 or 100 times a day that exert drag on a project. And I've seen this in my practice in my career, where junior programmers will have a lot of these convoluted things they're doing at the command line, and even when they can type fast, maybe especially when they can type fast, they'll just keep doing those things over and over again, instead of writing a script or a make target to automate those things away. Try to get things to be low touch or no touch where you can, because again, that frees you up, that decreases your cognitive loading, so you as the software engineer, as the data engineer, can focus on higher level problems, because that's where you bring the most value. Your value as an engineer is not as a typist, it is as someone who is juggling complex ideas and again creating insights for your customers. Automating these small tasks can give you large time savings. Again, something you do 50, 100 times a day without even thinking. If you automate that, if you streamline that, then you will find that at the end of the day, you have more time, which is good. Repeatability, right? If you're doing a lot of things manually, typing out complex command strings all the time, it's easier to introduce typos, and things of that nature. So if you make things repeatable, you're going to be able to jump into your code base, sling data, and get from inputs to outputs, and be a more reliable engineer. The factors we need to help our principals control, our consumers control, are time and cost and risk. Right, so things will always take time. They'll always cost something. And there's always a certain amount of risk, because some amount of new code is almost always going to be part of the picture. So the point is not to eliminate those things. The point is to give us better control over those things. Automation helps us do that. Automation forward helps us get things done faster, and precisely because the things we do in an automated environment are more repeatable, we cut down on cost and risk as well. Your defect rate goes down. If you have to generate SQL queries, for example, it's always better if you can use templates. Templating gives you a way to get results quickly, and it's less likely that defects are going to slip in, because if you've got structured data and you can feed structured data to a template, then you can count on the result. And that's better. Fewer defects over time. If we start from the premise that our processes, that our code bases should be well designed, our abstractions shouldn't be leaky, our sight lines should be clean, our functions should be as focused as possible to do one or two things, and that's it. These kinds of practices make it easier to automate things. If you take the time from the beginning to factor out your magic variables, factor out credentials, factor out whatever numbers you want to have as knobs to turn on this process. If your software design is good, then it's much more likely that you can automate things away. So you could say that automation forward thinking and good software design act as a kind of a feedback loop. It's self-reinforcing. As you get to appreciate the gains you can get from automating parts of your process, you're going to tend to write software in such a way that it's easier to automate things. And then that's going to drive you to think differently about how you plan out your next piece of code. And the result is better engineered data pipelines and better software engineers. So how do we put the Mercury method into practice? How do we maintain short feedback loops? Well, we stay in the code. This goes back to what I said earlier. As much as possible, we want to stay away from being mouse jockeys. We don't want to have to put in some changes and then jump out and go to a web console and click around. Sometimes that's necessary, but we want to stay away from that as much as possible. You stay in the code, you stay in the shell, you stay near the data, and you set everything up so that you can make some changes and see the results of those changes. We stay in the shell. Again, the shell is a piece of infrastructure. We have tools there that let us concatenate files, that let us transform files on the fly, that let us redirect the output of commands to other commands or to files, right? So we have so much built-in tooling, and it's there for us. You could argue that, Unix/Linux is almost kind of the perfect, it's almost like an operating system that was designed for data engineers. And that's good. So we want to stay in the shells, leverage that environment, leverage that tooling. Make your tooling an extension of your environment. This is, again, I touched on this earlier. All my tools tend to play nicely with standard in, standard out, and standard error, right? So that existing tools work right alongside my tools, and I can take advantage of whatever's been done before to get my results faster, and again, to be more reliable. Yes, I think I write great code, but the fact is that something that's been around for decades is going to be more reliable, almost certainly, than anything I can sit down and write today. So the tooling is an extension of the environment. The environment is designed to help us get the job done. So make it so that all your tooling plays well together and plays well with the environment. Again, context switching is expensive. How do we implement small, sharp tools? We start with a philosophy that things should be as simple as possible. We write single-purpose programs. Again, complexity creeps in all by itself. As the mission becomes more demanding, more technically demanding, the complexity will grow all by itself. If we can avoid adding complexity where we don't need to, then that's going to benefit us, even in the short run, but especially in the long run. We have a great engineering tradition in this operating system and in the tooling around it. And if we leverage that, then we can get things done faster and better because we have to write less code. It's as simple as that. How do we employ lists, structured data, and transforms? As software engineers, we're already familiar with the idea of decomposition. And typically, when we talk about decomposition, we're talking about breaking complex tasks into simpler tasks. But we can apply that same mental discipline to our data. If we can have complex structured data, then we can have relatively simple code that acts on that structured data. Turn lists into records or instruction sets. That's more or less self-explanatory. Treat our records as immutable as we write data pipelines. Our functional programming brethren like to talk about immutable data, right, and avoiding side effects. We can do the same thing, the same kinds of things they do and get the same benefits they do, even if we're not in a functional language. So Python is not really a functional language. We can use these principles. So as you'll see when we do live coding, I tend to write data pipelines in such a way that I emit files, and each file as I emit it is immutable. I don't change a file once I emit it. If I need to do a transform on that file, I'll read the file and emit a transformed file. Then the next stage in the pipeline takes that transformed file as its input. So every data pipeline I write pretty much looks the same way. They are lists of functional transforms. How do we operate in an automation forward way? Well, it's a challenge to kind of get your head out of your own process. Sometimes when you're deep in a flow, you don't want to stop and take the time to put this series of complex commands into a script that you can just run. The temptation is just to keep on doing it that way. it's not apparent that you're saving time. A lot of times you seem to be just burning time when you stop and say, hey, I'm going to write a script that can do this. And so to a certain extent, it's an article of faith that once you do that, it's going to yield dividends. But understanding when you need to do that is part of the art of software engineering and data engineering in particular, because you're doing so much data intensive work. So I can't stress that enough. You have to be on the lookout for opportunities to fold little bits of complexity into scripts. When you want that complexity, you just call it. Create and use templates where possible. I've talked about this before. I'm a big fan of writing code that writes other code, but the caveat is that I don't want to have to manage the generated code. That's very important. Not everyone likes this method, but I like this method because your outputs are very clear. It's clear to see what your pipeline is going to do. You can literally comment out the last line of your make target and the line in which you actually execute the generated script. And you can inspect the script. So you have an almost built-in preview mechanism. What is this script going to do? Right? So I'm a huge fan of generative programming. But again, what you don't want to do is use generative programming in such a way that the artifact that you generate is sensitive and has to be managed, and then you have to have something that detects changes to it. And you don't want that. You want to write your routines such that you can generate a script and blow the script away and generate it again, and it shouldn't make a difference to you. So to recap, when we're talking about data engineering, that is writing data pipelines using the Mercury method, we're only talking in part about using the actual Mercury data engineering library. That's the smallest part of it. The real core, the real foundation of this method is thinking about your work in terms of short feedback loops, right? How can I minimize the time it takes for me to see if I did the right thing? You have to keep your tools small, preferably single purpose, so that when you do have to open up a piece of code, you don't have to do a lot of digging. It's fairly evident in the first page or two what the code does, because preferably the code is only a page or two long, right? Keep your tools small, keep them sharp. Write your data pipelines in a modular way. I have not seen any good reason why a data pipeline should be monolithic. Most data pipelines are what we call ETL, extract, transform, load. Some people talk about ELT, whatever, but we're going to gloss over those differences for now. The point is that we should never have one giant piece of code that's doing our extract, our transform, and our load. We should always have those split into different processes. We should think in terms of lists, structured data, and transforms. Keep your structured data complex so that your logic can be simple. And then we should be on the lookout all the time for any process, any routine, any chore, any bit of toil, right, that we can turn into something that's low touch or no touch. Get the low level problems out of the way so you can add value by thinking about higher level problems, the insights that you have to create for your consumers. And that's the Mercury method in a nutshell.